let's get started here. Yeah, may Jesus help us to all learn well tonight. That includes me. So let's have a good evening. Anyway, let's get started. Should be. This is version 2 of this. So, but for a little bit of review, cores, and in fact, I am going to change this. So anyway, these are air core coils. These are some of my fun ones. I like these. This came out of an antenna tuner, as a lot of people call them. I call them a transmatch. I'm even having trouble remembering that tonight. Here's, oops. Here, these are air core. We'll put those aside. And this is a toroid. And with an air core like this here, oops, it's hooked up on that. Here, it'll create a magnetic field around it. And it'll go like this, and it'll spread out, and it'll spread out. And if you happen to have another coil next to it, that coil will pick up its signal. So you have to be real careful when you're building something to make sure you don't have two coils interfering with each other. But with these cores, the signal or the magnetic field is concentrated in the center. Very, very little magnetic field gets outside of it. So here's a little tiny transformer. There's two coils on there. And here's a core. This one has a, well, I was trying to say ferroresonant. What permeability. Help me out, audience.
I got nothing.
This is made out of
Iron.
no, it's not iron.
It's the one in your fingers is
Yeah, this and the core in here.
drawing a blank.
Anybody out there in the audience remember what these cores are made out of?
Is it ferrite?
That's it. Thank you, Bill. Oh, good. Yeah, ferrite. Yes, they're ferrite cores. And of course, remember, I told you before, there's all kinds of mixtures, and they're designed for different frequencies. This guy here, you see down the center of it, there's a little screw slot, so you can get little non-magnetic screws and screwdrivers put down there and adjust the reactance of this coil, which is this little coil right here. The slug that's in the middle screws in and out. This is a transformer, just kind of give you an idea of the size of it. And that has, it kind of looks like this in the inside. So I'm going to set these guys aside here. And I want to get out this. Now I think I'm going to switch cameras here. Okay, this is my higher camera. I can get more in. This is, I think it's a balun. It's for hooking up with your antenna. This is a kit. Daron built these. One day he did a thing on Zoom for people to watch. But here are the various parts for it. Nice case. And this is the coil and this is the core. Notice this one's much larger. This size of a core is good for about 100 watts. And you would wind this by simply going like this. And he gave specific instructions on how to wind wind the whole thing. But remember, if you go through like this, that is considered one turn. If you add another one, what goes through the center is the number of turns. So there's one, and then there's 2 turns. And if you add another one, that would be 3, etc. So anyway, this is a project that you can do yourself and have something that you can use with your HF rig and your antennas. So they're only $25. I have to check with Daron. I think he's got something up online that will help you to be able to take care of that. Slide. Okay, the radio, our basic equipment, chapter 2. Now, just for a quick review, this is our basic equipment. I mean, what do we use and why are we hams? We use radios to communicate. Especially if you're a technician, the very first radio you will probably have is a handheld radio. They're handy little things. Do we have one in here? I don't think so. To show, well, you saw them last week. They're especially handy for emergency communication. Or we have a noontime net here. And many of the people check into the noontime net and they do that just with their handheld. And some of them are doing it from as far away as Newport. They might have to step outside and make sure they orient their antenna vertically, and it works. And that's Newport is what, 20 miles?
18, 20 miles.
Yeah. So depends on whether you got line of sight or not. And for HF, that's for doing regional and distance. DX is long distance communications. Regional might be up to about 500 miles or so. And then beyond that, it might be considered distance. Hams, though, when they talk about DX, they're talking about talking to a different country. So if you're talking to, to Canada or Mexico, that's DX, or anywhere else in the world. So a lot of people get a lot of fun out of that. Now there's a lot of kinds of digital communications, mostly in VHF and UHF, but on HF, there's I think it's called FT8, which is a method that will actually pull the signal out from underneath the noise. Something, if you were listening in that spot, you would not even be able to hear it. And it'll actually pull it out of the noise.
And PSK31?
PSK31, that's pretty much noise level, I think. But that is a really good way to communicate digitally. It's like you're sitting and you're talking to each other on a teletype machine. You just type into it and the person on the other end reads your typing. If your signal gets the big negative with PSK31 is that it does not have any checking. So if something happens to the signal on the way, nothing will be corrected. So if you've got good communications, it can be just as solid as can be.
Yep.
Start getting noise, it'll start breaking up. Scott, were you going to say something?
Yeah, I was going to say also, there's a bunch of stuff on PSK31. You know, you could set up like if you're going to do a signal report, to where all you have to do is push a button, and then you just have to put 5/9. and the rest of it says this is your signal report and so on comes out.
Oh,
And,
right.
and you have one of those things. I don't know what they call those, but anyway, it's a shortcut that'll tell the person on the other end, what kind of equipment you have, or
They don't they call that a brag?
I guess so. And
Yeah.
then also the type of antenna, and then also what your name is and what your QTH is, and that just burps out automatically. And all you have to do at the push of a button, So it's pretty neat. You can do a lot of communication really quick, and then if you want to, a little rag chewing, and you can't do that with the FT8 and all that stuff. That's just signal reports.
No,
Just,
FT8 is very limited.
Yeah.
I mean, it's very slow. And so I think FT8 has, I think it's about a 30-second or one. No, wait a minute. I'm getting it wrong. It has an 8-second period. So one station will transmit for 8 seconds, or excuse me. Yeah, 8 seconds. Then all the stations stop. And then the other set of stations transmit for 8 seconds. And so it's on an 8-second cycle.
yeah.
But in that 8 seconds, you can get your call sign, your
location?
your location, which is grid square, and signal report. And they Scott, they don't send, you don't even send your name, do you?
Nope, I don't think so. But I don't do that. I don't mess around with anything that I can't send a short message on at least.
Right, yeah.
If I can't send at least a short message, a call for help or whatever, I don't want to bother with it.
So did you all say that PSK31 is text and voice?
No, it's just texting.
Okay.
Yep. And let me tell you, when you get, I'd encourage anybody to do a little bit of that PSK31 when you get a chance, because it's quick and it's a lot of fun. And I might mention, on 5 watts, I've reached South Africa with using PSK31 digital.
Wow.
Oh, wow, that is good.
And I'll bet Annalise knows how to text.
Annalise, do you know how to text?
Yep. There was text before texting was cool.
Yep. Yep.
Yes. Okay. Specialized, there's all kinds of specialized equipment for contesting, for EME, which is Earth, Moon, bounce. You actually send a signal from here, bounce it off the moon, and get it back. There's something like in the neighborhood about 300 dB loss in that process that you have to make up. So it takes a fair amount of power, and you can use computers. JT65, which is the predecessor to FT8, was used, and it would send a signal up to the moon, and people on Earth would be able to receive it, decode it, even though it was below the noise. But that would go for a full minute on each trade. So one person would transmit, and then it would start right on the minute. If you have an accurate time, whether from your computer that's showing computer time, not. I'm sorry here. I keep trapping myself. It's the GMT, Greenwich Mean Time, the actual time that everybody has on the Earth. so that at exactly the same second, all the same transmitters start transmitting. And then 1 minute later, it reverses and the other end answers. And in that time, as we said earlier, all the exchanges, their call sign, location, and signal strength. But having talked to somebody that's off of the moon, that's quite an experience. And anyway, there's television and there's all kinds of fox hunts. That's where you use radio direction finding to find a radio that's somebody who's hiding out. So lots of things you can do. Now, one of the things, and this is what we're getting into now, is how radio works. And transmitters, we're going to be talking on the transmit side. Oscillators, modulators, drivers, amplifiers, the whole works. We will talk about each one. And tonight we're getting into all the different kinds of parts that you find inside of a transmitter or receiver. There's RF amps, mixers, the IF, which is the intermediate frequencies, demodulators, audio. Well, we will be covering it all in time. So brace yourself. Now, this is, and let's see here if this is showing up. Yeah, okay, good. I need to move this kind of out of the way. Here is our antenna. But let's look at the receive side first. The antenna, the signal is a magnetic field that's moving through the air and it goes through the antenna. When it goes by the antenna, it induces a current into the antenna. And the impedance for most antennas, or well, many antennas, is 50 ohms. So if you've got a current in 50 ohms, you can figure out what the voltage is. If you have, for instance, 50 microvolts, which we've talked about in the past, that's an S9 signal, if you remember. So that is a voltage formed on this, which goes down a coax normally, or some kind of feed line. This is an SWR meter. We won't talk about that right now, but then it comes this way through a low pass filter. Now this is the radio. Remember, we used a radio to show what S9 was. It's a little 10-tech radio. We will be going through this radio extensively throughout this class. I used it for the last class I taught 12 years ago. So anyway, we go through the low pass filter, and then it comes up here through a band pass filter, which imagine when I say low pass, that means if we're talking about 14 megahertz, the low pass filter will probably cut off any signals that are 15 megahertz and higher. But anything lower than that would go through. When we got a band pass filter like this here, what it will do is allow, say from, and this is just a guess, 12 to 16 megahertz to go through. And what that does is it cuts out any extraneous signals. There might be a strong signal that's at 7 megahertz that would actually drive its way into the radio. But these filters eliminate that. Okay, or 21, anything higher than 14 megahertz would be cut off. So we come in here, we go through an RF amplifier. Here is the receive mixer. Now, what happens in a mixer is if you have two signals that go through an active device, it will mix them. So I probably should have thought this out beforehand. If you take this is a Well, anyway, this is the variable oscillator. This is a crystal oscillator. And this is a bandpass filter, which allows, with this here, this varies, which mixed with this gives you a frequency through this filter that varies. And when you come up here and you feed it to this mixer, it will go through here and it'll go through a crystal filter. Now, this is probably about 8 megahertz, this crystal filter. So the combination of this frequency, which combines to make a frequency, and then it mixes with the RF coming in, mix. You come out with 8 megahertz and you go through this filter, which then comes down here, it goes through an amplifier. Here's another crystal filter. This one says it's optional. That would probably be the CW filter. So this filter up here would be 8 megahertz, and that would probably be about a 2.8 kilohertz filter. So its bandwidth is 8 kilohertz based around 8 megahertz. And so that would let your audio go through. Remember, your audio signal, at the most you need is 3 kilohertz. And you can get as low as 1.8 kilohertz and still have reasonable audio. In fact, sometimes that's desirable to do to get rid of excess noise. So anyway, and then this filter here would be the CW filter, which would only be about 500 cycles per second bandwidth. And there's one thing when you got it, folks, something that I need to tell you, and in this class, I am not trying so hard to get you a license, although that would be a good thing. My main intent is to teach you about amateur radio. I'm 75 years old. I don't know how much longer the Lord's going to keep me here, but I want to get across to you as many things as I can, as I know about amateur radio, electronics, and how things work. So if it sometimes seems like I'm rambling on, I'm trying to do that job. And that's the reason I'm videotaping these, so that later, when I get even a lot worse, you will be able to go back and study them. And you'll get this. I'm going to try to teach you all the little things that I've learned that work. So hang in there with me. But anyway, right here, the narrower a filter is, the less noise there is. So if you're trying to pick up a CW signal and he's buried in the noise, if you go from a wide filter like this and not bypass this, you won't be able to hear it. But if you go through a crystal filter here, you will get rid of a lot of the noise and you might be able to hear the signal. So anyway, then you go through an IF amplifier. And then you go through what is called a product, for this radio, a product detector, which works with this BFO and the IF, and they mix together, and what comes out is audio. And the audio is then filtered through, it's not filtered, it's amplified, comes through here. This indicates a volume control. And then here's your audio amplifier, and here's your speaker. So that is how a radio, a basic radio, most of them function today. And this radio is probably 40 years old. But they all pretty much work this way. Now let's talk about, hang on a second. Let's talk about transmit. Right here is the microphone. And there's a mic amplifier that takes the 5 millivolt audio signal from the microphone, amplifies it. Here's we call these pots, a volume control. That's a variable resistor. And then it's amplified again. And then here's the beat frequency oscillator. That audio is mixed with this signal, which puts out an RF signal here on this side that is modulated with the audio. So that comes down here, it comes up here and it goes through a filter and it will limit the bandwidth of your audio. It goes into the transmit mixer, which, okay, now here we've got one frequency, and we will get into more details about mixers and how they work later. But here again, we've got the variable oscillator. That's our tuner. That's how we tune around and we find different stations. It has a mixer that works off an oscillator to create a specific frequency. And this, by the way, will have a 5 kilohertz spread. Most of your or many of your bands have a 5 kilohertz spread. If you take 80 meters, for instance, it starts at 3 megahertz and it goes to 3.5 megahertz. If you take 40 meters, that starts at 7 megahertz and goes to 7.3. If you go to 20 meters, that's 14.0 to 14.0, no, 14.350. That's 350 kilohertz. So this VFO, variable frequency oscillator, here gives you that much bandwidth at this point here. So your audio and one of your RF signals comes through this filter, goes to this mixer here, that then takes it up to the frequency that you're actually going to transmit at. So at this point here, this is the frequency you're transmitting at. You go through a bandpass filter that cleans up a bunch of stuff that may have been created in these mixers. And I'll explain that later. Through an RF amp, here through this. Now this amplifier has the ALC on it. That's automatic level control. If you come over here and you look at this SWR meter, there's a circuit in here that senses how much power is going out. And what it does is it gives you feedback that comes back to the automatic level control that then controls this amplifier here. So if you're talking on your microphone and you're talking like this, and then all of a sudden you start talking like this, it will keep you from driving your output with too much power. So anyway, this controls the amplitude of your signal. And then you go through an amplifier here, a power amplifier here, which then goes out through a low pass filter that eliminates a lot of stuff that we have generated that we don't want to go out over the air. And it'll go through this SWR meter and then out the antenna and transmit. Everybody totally understand how our radio works now?
Question.
Yeah, just hang on to the question for a second. Now that I've woke you up,
I'm awake.
are you?
Yeah. I'm studying the chart here.
Yeah, good. Yeah, Scott, Bruce.
The other guy, yeah. So what you're telling us is each one of those components does potentially cause a little bit of interference.
Yeah, every time you go through a
mixer.
yeah, I mean that's the
Amplifier.
ones. It depends on the amplifier. Some of them create a lot of garbage. They're class C amplifiers. But if it's a class A, it usually comes through pretty pure. But when you mix two signals together, let's say that you run through this mixer 14 megahertz, and you're trying to get to 8 megahertz here. So your local oscillator that's coming in has to be, well, let's go above. The local oscillator has to be 6 megahertz above this. So this output here, and this is just a guess on my part, but it would work. The output of this here has to be 20 megahertz, which is 6 megahertz above 14 megahertz. But when you mix those two together, you will get out of it 14 megahertz, 20 megahertz, and 8 megahertz. And every other single combination that you can get from any of those frequencies. Each one dropping in power as they get farther and farther away from the correct frequency. Did you follow what I said?
Vaguely.
Vaguely. Oh, okay. But let me say it again. When you mix two frequencies together and say we got 14 megahertz coming in, we want to have 8 megahertz. So if we have 20 megahertz coming here, 14 from 8 is 6.
You got it.
Or say the difference between, 14 megahertz and 20 megahertz is 6 megahertz. Oh, how did I? Now I did that wrong. Excuse me, Bruce. Was not expecting this question nor dealing with this right
Sorry.
at the moment.
Should have asked you a different
We
question.
need 8 megahertz.
Yeah.
Right. So it would be 22 megahertz. Excuse me.
We're all human. Thank
So
you.
It goes 8 on either side of 14.
Uh-huh.
No.
6 or 22.
Well, that's why. Now wait a minute. We got 14 and 22. We've got 8 plus or minus from 20 megahertz. So we end up with an 8 megahertz signal, which then goes through this filter here. But in the process of doing that, you get all kinds of extra frequencies that you do not want. So that's why you go through filters to get rid of that excessive stuff.
Now, do filters add into this as well? I mean, as far as causing?
Normally, no. No, they should be pretty straightforward. The signal you want is what will go through, and they will not generate
Okay.
other things. You've heard of a triple conversion receiver?
Yeah.
I think most hands have, and many of the radios out there today have, they do a triple conversion. My little IC 735 is a triple conversion receiver. Its first IF is 70 megahertz. 70 megahertz. And then it goes down, I think, to 8, and then it goes down to 455 kilohertz IF. So but each time it goes through one of those stages, it generates a whole bunch of other frequencies that you have to control and deal with. Did that answer your question?
Very well. Thank you.
Any other questions about what we're doing? Now, this thing on the mixers, I might be a little bit confused on the frequencies, but we will be discussing that in total detail later. And in fact, we will actually show it on a software defined radio that shows up on a computer. Excuse me, and it will show the screen on the screen of all the different frequencies that are generated by something like this. So we'll actually get to see it and then show how we deal with it with filters, filter, notch filter. I mean, there's all kinds of filters, low pass filter, band pass filter, so on.
Joe,
Yes.
just this is Bill. Can you explain like how is a filter built? What is it made of? Is it built from inductors or what's inside a filter? That how do you make one?
Coming up. Each one of these sections is a filter. Say we got, here's a relay, here's a coil, and see there's 3 capacitors here.
Yeah.
Here's a relay. So what happens, each one of these is a different band as we go down here. So when we switch bands, we turn on all the relays except for one set, which turns the signal that is, let's see. This is the input, and where I'm trying to figure out. The output of this, and this is the ICOM IC735. The output is right here. So the input comes in here, and then it goes through one of these filters here. So your question was, what are the parts? In this case, we've got 2 inductors, 3 capacitors. 2 inductors, 1, 2, 3, 4, 5 capacitors. But these capacitors are actually, they're just hooked in parallel, so they're just adding up. So anyway, does that give you a better idea?
Yes.
Okay, good. The reason I'm talking about parts tonight is so I can explain how these work. I mean, we've been talking about coils, right? Here's an air core. And this will be the highest frequency. So this is 28 megahertz across here. Now, here's a core that has the most windings, so this has the most inductance. Oops, excuse me. Get this over here where you can see it. These have the most inductance, so we can know that these are there's 1, 2, 3, 4, 5, 6. Yeah, these are 160 meters, or 1.8 to 2 megahertz. So this band pass here works from 1.8 to 2 megahertz. And we've got the big coils and lots of capacitors, big capacitors here. So this works at a lower frequency. And this particular arrangement is called something specific. I can't remember what it is, but before the class is over, you will have learned at least the name of this filter. Any other questions? Nope. Okay.
I'll bet that was a pi filter.
Do you think that's what it is?
Yeah. Got your coils with capacitors on each side.
Actually, I don't think that's what this is. But because typically a pi filter is changing inductance. Like if you have a tube which has about 2,000 ohms of impedance,
Uh-huh.
an antenna that's 50 ohms of impedance, that's what you're doing with a pi output stage. So now let's move on here. Now, well, I'm not going to ask, but hopefully those of you who are working on your licenses are following these recommendations for your reading. Now, for this class, I am not just going to cover the extra material because that assumes you know the technician class and general class license. And honestly, most people don't know it when they take their test. I mean, they've studied and they've got the words and they've got a familiarity and they've crammed, they take the test and they passed it. And that's wonderful. But shortly after that, it's gone. You know, you really have no idea what you learned. And it takes a while to build the confidence and the experience to figure out what's going on. And so hopefully in this class, we can build some of that experience and understanding of how stuff works. But for the technician, you should be reading in 3.2 in your license manual. For the general, 4.3, that's basic components. And the extra is in 5.1. Okay, now I want to show you this guy here, and shortly I'm going to show you another one. Now, how many people got my email today with one of these?
Yes.
And I probably sent one that ended up at Glenna's email, and she has now told me 3 times to use Bruce's email.
Yeah.
But unfortunately, and I sent her an email apologizing today. For some reason, the program just picks up on the one that was always sent before. And I need to try to remember when I go to send something out to change it. Hopefully, eventually you'll learn not to send one to Glenna instead of Bruce.
I keep hearing about it too.
Oh, really? Is she giving you a bad time?
Oh, yeah.
Oh, for crying out
I'm
loud.
going to print it out and use it as wallpaper.
Ah, good plan. I'll do
Well, see, the internet knows which one's going to pay attention
that.
to the email.
Yeah, well, tell Glenna that I'm sending it to her because I expect her to take this test.
Oh, man, you opened a can of
She'll
worms
give you
on that
some,
one.
she'll give you some resistance.
You opened a can of worms on that one, Todd.
Yeah, this is one chart, and this actually comes from the technician, and it's somewhat simplified to the one, but here are all the schematic symbols for all the different parts. So next, we have this, and this is what I sent out to all of you. Now, notice here, upper left-hand corner, these are all different kinds of resistors. And so the variable resistor we call them POTS, which is short for potentiometers. It's a variable resistor. That is different than an adjustable one, which is usually you move it to a special location, clamp it down, and it stays at that resistance. So, oh, excuse me. Yeah, this one's tapped, but you run into few of those. Capacitors, here are capacitors, and these are the symbols. Remember, 2 plates. So, and here are inductors. Here's an air core inductor. Here's an iron core inductor. Do they have a ferrite? I don't see. But this is one of the little ones that you use a little screwdriver and you move the slug, the ferrite slug in and out.
Doesn't the bottom left say ferrite?
Yeah, it says ferrite bead.
Oh, okay.
Now, a ferrite bead is one of the toroidal ones, except it's tiny. And the hole down the middle of it's big enough to run a wire through, and that's it. And it might be a whole 1/8 of an inch or 3/16 inch in diameter. But what you do is you slip it over like the lead of a transistor, which helps keep it from oscillating. So those are our three main components. And then it used to be there were tubes. And I want you to know I cut my teeth on tubes.
Ouch.
Blur.
Well, that was better than other things people used to teeth with, but anyway, this is a triode. This is a pentode. It could be a tetrode if you remove this element right here, the top element. And then this is a heated cathode. This means the filament is actually the cathode. Here you use a filament to heat the cathode, which is this thing right here. So from there, where are the transistors? Down here. See this area here? These are all the various kinds of transistors. Here's an NPN and a PNP. And so here's P channels. These are all field effect transistors going across here. And then these are N channel field effect transistors. We don't need to know at this time what they are. I'm going to have physically, I'm going to show you some of these. But hopefully in time, we will get to the point where you'll see a part, you'll be able to name it, and you will know what its symbol is. And here's something that we should know. These are not transistors, transformers. These guys here. So here's an air core, and here's a well, this is ferrite core.
Sure.
Well, that's also an iron core. Same symbol for an iron core transformer. So you got either one of these sides could be the primary and then a secondary. And some other device. Now these here, these are diodes. And this one, LEDs, light emitting diodes, which when you run a current through them, they let out light. Yeah. And a Zener diode is something that we will be studying more. And there are Schottky, tunnel, and all these specialized diodes. Triac, that's used in a light control. When you vary the brightness of a light, you use a triac to control the light level. Here's a bridge rectifier, this is the schematic symbol. This is more of a drawing, but you have the AC coming in on both sides, and then you got the negative and the positive. And we'll get into how that works later in the future. So outlets, you've got outlets. Here's an outlet, and then this is a plug. Anything else?
You might go over a few of the switches.
Oh yes, yeah, switches. Thank you.
Mm-hmm.
Switches. Let's just start with SPST. That's single pole, single throw. But here are the two contacts. You'd have. I accidentally clicked on it. You have a lead coming in here and then a lead going out here. And when the switch is open, nothing could go through the circuit. When you close the switch, in other words, from here to here, it makes the contacts and things work. So this is single pole, single throw. This is single pole, double throw. And you can take this and make it double pole, double throw, which means you'll have two of these. And Bruce, that little bag, and John, that little bag, you'll see a little red switch in there.
Yeah,
That's a double pull, double throw switch.
can you give an example of what that means? What would you see in a house application for a double pull, double throw? Or in a radio? Either
And in a house, you'd have a single pole, double throw, which that would be your three-way lighting.
Okay,
And your normal house switch, which for your light is a single pole, single throw,
yeah.
just two connections on it. There are many applications, just the power switch to turn the power on and off for the radio is very often this, but today, honestly, you don't switch the power to the radio that way anymore. It has a it actually will have a single gate oh, my mind's going blank.
Instead of switching the radio, is
Try.
I think, Joe, what you're maybe searching for, instead of switching the complete power to the radio on, you'll probably switch just a relay, a low voltage relay, and then that relay will close, and then the main power can go through the other contacts.
Yeah, what
Is
you're
that what you were
saying
looking
is
for?
true, and that's actually almost becoming old technology because people use field effect transistors, isolated gate IGFETs to do the same thing.
Mhm.
So in a lot of applications, people are totally getting rid of the mechanical switch. So they, if you have a normal transceiver, it will draw about 20 amps at 100 watts. You got to have a pretty hefty switch to handle that 20 amps. They have found that they can use a relay or use a field effect transistor to switch that, and then use a little tiny switch to turn it on and off.
Yep.
So we're John's back there giving me the big circle about how much time I've got left. It's break time, folks. Let's take a break. In 10 minutes, we'll come back and get started again. Radio the guts. Okay. Now, this is a Bofang radio. It's a handheld radio. And I want you to take note of the various things. Now, this is the antenna connection. Here is, I think, the volume control. And these are the parts. And you can see they're tiny, tiny parts. Now, imagine that's about, this whole thing is just about the size of your hand.
Yeah.
And so notice these tiny, tiny parts. We're going to get into a lot of that here coming up real shortly. So, and here's the keypad. You know, and there's integrated circuits. Here's an integrated circuit. These are resistors. Here they got their, and that's a capacitor there. Here's another integrated circuit. Here's, I think this is a coil right here. Might be, yeah, it looks like a coil. So anyway, and here are more integrated circuits. And anyway, there's lots of little tiny parts in it. And that is so much better than what we used to deal with, which were through hole parts that had wires on them, and you have to run the wires through the PC board and solder it, and things were much bigger. So now I'm going to stop sharing here, but I want you to notice this PC board out of a ICOM 7300. Now that's an HF radio. It goes from 1.8 megahertz up to 50 megahertz, which is 6 meters. So it goes from 180 to 6 meters. And this part right here is the transmitter. You have the output transistor, a transformer right here. That's the output transformer. Here are two FET power amplifiers. And here's the driver for those power amplifiers. And this is the driver that creates the power to run these, which then puts it out. And then the output of this goes over here to the filter section, which you should recognize. So let's escape this. These are 3 tubes. They're called 811s. These are very old tubes. And I just measured all 4 of them on a tube checker that I built for testing transmitting tubes. 3 of the 4 of these are good. Well, we pulled it out of an amplifier, and that amplifier weighs about 80 pounds, and most of the weight is one transformer. And that transformer is dead shorted. And did anybody see what's you're sure you haven't got yourself blanked?
My camera's off.
Oh, what? Come on, John, you got to give us a show. Anyway, we've decided, I have decided we're not going to try to repair that transmitter. It's still got a lot of good parts in it, but Scott, this is for you. You want a transformer you can rewind?
The amplifier?
For that amplifier, yeah. If you want the amplifier, you can have it. I'll even throw in the tubes.
I'll start it to your front door.
I don't hear him saying anything.
Wonder why.
Ah, what a disappointment.
He's muted.
Oh,
There he goes. Look, nope.
Did the amplifier use 2 or 4 of the 811s?
4.
Uh-huh. Wow.
2 of them check really good. 1 checks okay, and the other one's completely dead. And I think the reason is the cap, the wire that goes up to the cap might be broke because it shows absolutely no output.
Uh-huh.
One of the caps is off, but anyway, I don't know. You think you might be interested?
Might be.
Okay. Well,
What frequencies? That'll handle.
I think it's at least 80 through 10. It might be 160 through 10.
Yeah. I don't know.
It's a Gonset.
Oh, wow. Boy, that's a good old name. Ancient name.
Yep. Okay. Now next. Now remember when I talked about power cords? Remember I showed you one that was bad? I was actually hoping I could find it here. I'm not sure where I put it. This is a good one. And I want to show you the features. Yeah, no, I don't know what I did with it.
take it out of your trash can. Maybe it went in there.
No, I would have saved the wire. Okay, this is an ICOM. It has this connector that fits most of the ICOM radios. Now notice, here's the radio end here. See where the two fuses are, and see the kind of fuse that it is. These are real heavy duty fuses with good connections. And then that goes to power pole connectors. And this is the way that your cable should look, although you might not have fuses at this end if you've got other fuses farther down here. So anyway, that's the way it should look. Now, thinking about cables. Yeah. By the way, these cables, these power cables, if just right off the top of my head, I'd say 20% of the problems you have with HF radios are bad power cables. And when somebody brings me a radio and they want me to fix it, I tell them, you must bring the power cable, the microphone, and the manual. I want to see all three of those things, because many times the problem is not the radio, it's this. Because there's a bad connection in it. And when you're trying to draw 20 amps to produce 100 watts, things break down. So, and one of the other common problems you have is bad coaxial cables. Now, can I get this to focus? No, oh, maybe I can here.
Here it is.
Okay, notice just the white there, and there's a little bit of copper wire. There's no solder.
Yeah.
Absolutely none. This cable I would not trust for anything. In fact, the way I would deal with a cable like this,
Turn it off.
is just like this.
Why? Why wouldn't you just solder it?
Oh,
Wait. Oh, Joe.
You like to destroy things, don't you, Joe?
I have more fun cutting things up. Yeah, you could solder that. Yeah, actually, this one you can see the wire in there, but I'm not sure because the wire. Yeah, no, Scott, that's not going to work with this.
Huh.
This one, the adapter. Well, this does not have it. Yeah, that is just not. I'll tell you something. There's a garbage can behind me. And that's where it went. And I want to show you this.
You just say you wouldn't throw cables away.
Didn't you?
Yeah, I just did. I just changed my mind.
He can hear pretty good.
Look at this.
Oh, yeah.
Look at this solder
Oh,
connection.
selected hearing.
Yes.
That is a good solder connection.
Ah,
So you can tell that it's been well soldered, and it's a hot solder joint.
so you want to do it on all of them, not just one.
Oh yeah, if you're going to do it, you need to do it correctly, and that's solder them all. One, it helps keep moisture out a little bit, but mainly it makes a good connection to the coax. Now this one I would not have any problem picking up and putting to use. And this is RG8X. I don't see.
There it is.
Does that say 8? Yeah,
Yeah.
I got to turn it around this way. RG8X. So that's a good cable. It'll handle a fair amount of power. Not 1,000 watts. That's not what this is intended for. But this would be a good jumper cable. And whenever I get one of these cables, first thing I do is I spin these things off and look. One of these Yeah, what happened?
It's got silver plated connectors too. Probably Amphenol.
Now, see this solder joint? Look at here, not soldered, not soldered. Kind of soldered. But you can see, see the edge right around here. And it's not actually soldered to this. So what they did is they applied heat here. They got enough heat for the solder to stick inside, but it's not sticking to this connector itself. And
Cold joint.
see this blob?
Yeah.
This piece here, the PL259 did not get hot enough to take solder. And that's what you call, and this is a grossly cold solder joint.
Mhm.
And it will fail.
Mm.
I mean, it's just it. And when you start having trouble, you don't know why. Same thing. I mean, see, here's the same thing. See, it's all blobbed up.
Some amateur did that.
Yeah, I've seen that kind of stuff even from professionals. But anyway, see, notice the difference.
Yeah.
So this is a hot connection. Now, in order to solder one of these, and I'll have to admit, I knew one person who could do it with a 125 watt soldering gun. But you need a very large soldering gun that produces a lot of heat and produces it fast.
So we're talking 120 watts?
Oh, I knew somebody who did that. That was
500
Watts.
this. Oh, it doesn't. It's lost its labels. This is a 325 watt soldering gun. This one is, I think, 125 watts a maximum. 90 watts and 125 watts. You can see it right here. Wait a minute. 90 and 125. This is not hot enough to heat. This is not hot enough to heat this. This is a lot of mass. And you have to get this part here hot enough that it'll melt solder, which means it needs to be about, what, 500 degrees Fahrenheit, I believe, something like that. Anyway, but this soldering gun is 325 watts. It's a real heavy iron, and it will pump enough heat into this to solder this. Now, one of the things I've learned is, and I have a difficult time with this, but I have to heat this hot enough to melt the solder so that if you apply the solder directly to the metal right here, it'll melt the solder. But it also has to heat this shielding that's on the inside. Problem is with a small gun like this small gun, is you have to keep applying heat and keep applying heat, and pretty soon this entire thing is hot enough to melt the solder. Problem is it also melts the insulation inside your coax cable. Honestly, I prefer crimp cables. I've got all the tools and everything to crimp, and I only do a solder. I only solder these things if I have to. I mean, if you have this style of connector, you have to solder it. In an emergency, you can stick it together and work for a while, but give it a month and it'll corrode and it'll quit. So let's say that's lesson number 2. Now, lesson number 3. This is a meter that my friend Alex donated to our club. And he did not have these probes. He gave us, actually, he gave us these probes. But notice the covers that are on here. Each one of these has very sharp points, which when you're trying to test something, that's very handy because you can easily scrape through the corrosion that's on there and get to the actual part that you're trying to test the voltage on or the current or whatever. But the problem with these is they're quite fragile. And if you drop these on the floor, very often this tip will break off, which you don't want to happen. So they have these little protectors here. And honestly, people, if anybody wants a set of these things with broken tips, I can probably provide you with 2 or 3 sets. But here are 2 that I have. I forget, these are somewhere in the order of magnitude about 4. I think they're about $4 for a set. They're inexpensive, but they're sharp, and you break them easy, but they're inexpensive.
So probes are pretty standardized as far as their size.
Yeah, these plugs here, any of your modern meters, these plugs will normally fit. These banana plugs. In fact, notice this here. And let's see, come up here, see this circle? And then there's the inner circle, and I can see it. I don't know if you can, but there's metal inside of there. And when you put this on, you can see the banana plug. This is called a banana plug here, right here, which makes contact with the metal there. But all this shielding keeps, if you accidentally get across a couple thousand volts, it helps keep you from getting zapped. So anyway, these I'm donating to the club, and if somebody needs a set of probes, $4. There's a box here for you to put your money in. Put a note down what you got, and how much you paid. And by the way, that box, I mean, there's so many things in here that I've brought in here that can go for free. And you know, if you got some money, you can donate a little bit. It really doesn't matter to me. I know there's some people in the club would get upset with me talking like this, but if you got a project and you need a part, man, this place is loaded. And if you can't find it here, come to my place.
You will find it there.
So, well, I've been trying to get this place equipped just the same. Now, okay, this is a desoldering tool. This is a 40-watt iron. As you can see, there's a hole in the tip. And you can press this down here, and you press the button, and it sucks air up through here. So you put this tip on where you want to pull the solder out of, press the button, and it sucks the solder out. I'm donating this to the club. It was like, I mean, it was a whole, I think, $10. So we have this here. So if you need to desolder something, a very, very handy tool to have. That was a new product I saw, and I bought one for myself also.
It beats the old balloon squeeze kind.
Yes, yeah, and I have desoldering tools that don't have an iron on the top. They just got a tip, and they've got this, and you do this. But very often you've got your iron in there, and then you've got this, and you're trying to get it to suck, and it won't. It's hard to get to suck. This, I'm trying to. This is a supercapacitor.
Wow.
This is 4 farad, not microfarad,
Not
farad at 5.5 volts. Trying to, so we can see. You can see 4 farad right here, 5.5 volts. These are used in radios as a backup power supply to provide electricity when the power goes out. But this is such a large capacitance capacitor that it will maintain the voltage for a considerable period of time when you're working with modern typical integrated circuits. Because most stuff nowadays draws very little current. So this can be used for a backup battery for a period of time. And this was I think $3 or something like that. They're pretty inexpensive, but it's a handy tool. And most stuff runs on 5 volts this day. So with the 5.5 volts, you got a 10% buffer. So anyway, that's something else I'm donating. I got 2 or 3 of these at home. Took advantage of the sale. Now, back to the rest of our project. We're going to go over resistors again. Now this was from my last amateur extra class. Good. Notice here we got power resistors. 10 watts, 10 watts, 5 watts, 2 watts, 1 watt, a half watt, a quarter watt. These guys up here, these are half watt resistors. Here's a quarter watt. And guess what we've got there? Those are chip resistors. Surface mount device, SMD. These are the kind of things you find in your modern radios. They are tiny. And remember what we talked about last week? These have, see these leads? Each one of those leads is an inductor. So if you get to too high of frequencies, the length of these leads becomes a problem. So you want to make sure that if you're using these, you only, I mean, you solder real close to the board if you're using high frequencies. These here are wire wound, and so these guys here, which are power, and they need to be wire wound in order to handle the power, are inductors as well as resistors. So keep that in mind. These are carbon resistors. And these are deposited, they're not carbon like these, they're something else. I can't remember what it is, but anyway, now surface mount resistors come in long strips like this. These are just short strips, but you can buy sets of resistors. These are 1% resistor. Every 1% resistor that there is from 0 ohms all the way up to 5 million ohms, and not even pay $20 for the entire set. And the one that I got this one out, there were 3 of these, 2 or 3. I think there are 3 of these in each slot. So this is 430 ohms. And there were 3 of these, and I bought that set for, it might have been on sale for $8, or it might have been $12 or something like that. They're very inexpensive. Where you buy stuff like this, and they're 20, 30 cents each.
But they'll do the same thing.
Well, basically, yes. As far as resistance is.
Yeah.
But of course, this is a very low power, and that's a much higher power. But anyway, so those are our resistors, and they come on long rolls. I mean, this is just a short little piece that's been cut off. And they're 1%. They're very accurate. So let's move from resistors to capacitors. And I think for this, I'm going to that's that. No. Oh. Here we go. Let's have some fun. These are capacitors. And of course, we've already talked about inductors. So I've shown you lots of those. But, anybody want a flying saucer? Oh, yeah. We'll talk about those in a little bit. The only thing I don't have in here. Oh, yes, I do. Here's one.
The switch.
A disc. Oh, I do, don't I?
You see?
Oh, yeah. Well, speaking about switches, here's a double pole, double throw switch. Here's a single pole, double throw. And here's a single pole, double throw. And this is the common, and that's the common. And so this is called a double pole, double throw. And notice that the switch stops in the middle, which means the middle is off. And this way, these contacts connect to these contacts. And this way, this contact connects to that contact. And this is a 7203 0.4 volt. I used to 0.4 volt amperes. This switch has gold contacts, which means if you're using it for very low level signals, like your audio switching, your RF receive switching. But if you hook this up to your 120 volt and try to run your transceiver with it, you will blow all the gold off, and it won't be good anymore. But these gold contacts are really good for low level switching. But
Hey,
that's
Joe, I know you want to go to caps, just real quick though, because on my computer anyway, there's a delay between what you say and where you point. So by the time you're finished pointing someplace, the pointer hasn't caught up with what you're saying on my computer anyway. Can you just go a little slower and say what the position is and which contacts it switches to when you switch it in which position?
right. The people that out of here
Yeah,
get it all at once.
okay,
There's no delay, but there's a delay with what's coming up. You should be trying to watch it up here.
okay, all right.
But anyway, okay, but let's do it again. Here is a double pull, double throw. Here's a single pull, double throw on this side. And then on this side, here's a single pull, double throw. The center ones are the common contact. Now, with this switch in the center, neither one of the contacts make contact.
All right,
And most of these switches don't have a center. They're either here or they're here.
yeah,
But you can get them so they're center off. And then you switch down here, and what happens is inside the rocker goes like this and connects this contact to this contact. And then when you switch the other way, it connects this contact to this contact.
so the center contact to the outside,
Correct.
okay,
That's the common in the center.
okay,
And then, of course, the two sides are totally separate. You can get this in 2-pole double throw, 3-pole double throw, 4-pole double throw. So you can do quite a bit of switching with that, with these little guys. I used to be the switch evaluation engineer at Tektronix. This is a disc ceramic capacitor. And this is probably one of the most common kind of capacitors. They go from this size, which is very small, to this size easily. This is a transmitting capacitor. You will find this guy at the output of a linear amplifier like that one back there, 1500 watts. It's 3 kV and 0.005, I think. Yeah, 0.005. So this will handle a tremendous amount of voltage. And it is designed to handle the currents for RF. This particular standard disc ceramic capacitor probably will not handle much current, RF current, which will generate internally, it will generate heat. So, and then since we're talking about those, we'll talk about these fun ones. By the way, this is called a doorknob capacitor for kind of obvious reasons. This one is 441, that's 440 picofarads or microfarads. As I used to say when I learned, it was called microfarads. Somebody decided they didn't like that, so they changed, instead of MMF, they changed to PF, picofarads. So, and it is a 40,000 volt. So there's a high voltage that you can have between these 2 points. And this will handle a lot of RF current. This is this one. Now this is, by the way, this is the capacitor you will find in Russian equipment. And this is a 2200 picofarad capacitor at 10,000 volts. 2200 picofarad
And where did you say you'd find that?
in a Russian transmitting equipment. So when Russia collapsed and many of the nations withdrew, there was a tremendous amount of surplus material left behind. Well, I apologize for this. I I don't even see it like that, but boy, on the camera, it really looks bad.
Yeah,
But anyway, so these two, in fact, all three of these would be used between the plate of a transmitting antenna amplifier, 1500, 2000 watt amplifier, and the outside world. And after this, you'd have a pi network that would convert the high voltage that would be on the one side for a tube to the low voltage that would be for the coils and the capacitors, the coil and the capacitor that would convert this to 50 ohms for a 50 ohm antenna. And that's something, don't worry about it now. We will explain it later. Well, at least the best I can. So those are those capacitors. Now there are several other kinds here. Here's a typical trimming capacitor. You'll find these little guys in Tektronix oscilloscopes. This particular style, but here's a slot, and you can turn them like this and change the capacitance. Here's one that this makes it a little easier to see because you can see each of the blades, and this side over here is separated from this side here. And as you, oops. Okay, you guys need to tell me when my hand's in the way. Notice the openings here, right across here, and over on this side it's closed. And so as we twist it, this side opens up. And if you look this way, you can see there's just a tiny amount of overlap. So this would be a minimal amount of capacitance here. And then as we turn it, we mesh the plates together, so we increase the capacitance until it's there when they're fully meshed, and that's the maximum amount of capacitance. Oh, okay. All right.
we can discuss.
This is a mica capacitor. If you are working in transmitting gear that's older, and especially the tube kind, you'll find this kind of a capacitor in there. They're very stable, and they're well, I don't know, they're very stable capacitors. These capacitors are electrolytic capacitors. Here's 5,000 microfarad. Now compare that to, what did I do with it? This is considered to be a large capacitance, 5,000 microfarad at 16 volts. This one is 100 microfarad at 250 volts. So this is way smaller capacitance. And then we have here can anybody, oh, here we go. This is 1 microfarad at 16 volts. And then this one is 4 farads. Microfarad, this is 1 microfarad, this is 4 farads. capacitance wise, this is a huge monster compared to these, but it's a storage device, right? And if it's huge, it'll hold electricity for quite a while. And then here's a trimmer that's got a couple inductors on it. The same kind as the little one I showed you earlier. And it's got a potential, oops. I was going to turn that. Maybe with the screwdriver. We can see it opening up. Then we get around here where there's the plates are minimum. So, and I have one more. Well, actually, here these are surface mount. So little tiny leads, little tiny. And then there's this. This is a feed through capacitor. What you do is you mount this on the side of a aluminum housing that you've got it, and then the signal goes through here. What it does is it keeps like a RF, high level RF from coming out on this side over here. So anyway, that's it for tonight. We will get into a lot more stuff next week. The details of these parts and how they work together. And have fun, I hope. I'm actually enjoying teaching this. This is, to me, this is the fun part. So
Thanks, Joe.
anyway,
Thank you, Joe.
Thank you, Joe.
Thanks, Joe. It was
Yeah.
a good meeting.
Thank you.
thank you, Annalise. All right, let's see here. Oh, everybody's saying good night already. Good night, Scott.
Have a good one. And thanks a lot, Joe.
Oh, hey, if you do have interest in this amplifier, let me know.
Okay.
Because it,
Whereabouts is it?
it's here at the barn.
Oh, okay.
I mean, it's a monster. I mean, it's 80 pounds, but there's a lot of. If you come, we'll open it up. And you can see what's inside.
Okay.
Minus what the mice left. That's gone.
Yeah. Oh, yeah. We took out the mice, the nest,
Ah,
and that's not
good. Good enough. I'll have to take a look at her.
okay. All right. Good.
Thanks.
All right. Good night.
Good night.
All right.